Hi everyone. This is what we've worked with in the last video, and in the last video I actually did something accidentally, which is keep this size as 10 and just give this 4 elements, let's say 4 here, um, and let's see what happens in this case. Let's do a gcc arrays.c -o arrays.exe, and as you can see, this didn't give me an error. This array is just of size 4, and here when this loop runs 10 times, it's going to actually try and access the 5th element, the 6th element, 7th, 8th, all of those elements. So this still didn't give me an error, and let's see what happens when I try to run this. It gives me some random value, which is -39460. So the reason this happens is because C does not perform something called bound checking. So C is not responsible, the compiler is not responsible for taking care that you don't try to read elements which are out of bounds for the array, and C also doesn't take care of when you try to write elements to an array beyond what is allowed. So even if I had done something like ARR of I equals 0, and if I just get rid of this thing, even this is not something that C would give me an error for, but this is something that I should be very careful about, because what happens is an array is just created wherever C finds space in memory, and beyond the memory that's allocated for the array could be any data that could be important to you. So even that is going to just be overwritten with these zeros right here. So this is something that you need to be careful of, and also something that you need to remember. This is a common question that people ask. Does C perform bound checking? It doesn't. So that's one thing. And another thing that this reminds me, since I talked about memory, is how these arrays are stored in memory. So arrays in memory are stored in continuous memory locations. So since there are 4 ints in this array, these are going to be stored in consecutive memory blocks. So let me just show how this works. So if this is my memory, my first element will be stored here, my second element will be stored here, my third will be stored here, and my fourth will be stored here. So that's how it's going to work. It'll never do something like store the first here and then store the next one somewhere over here. So that's how they're stored in memory. And another thing that I want to show you here is let's just first get rid of all of this, and what I'm going to do is a printf and a %p. The %p actually gives away that I'm going to be printing a pointer, but here let me just give the name of the array. I just write ARR. So let me just make this size actually, and let's just go ahead and compile this. So as you can see, I actually got an address here, and which means that the name of an array stands for an address. And what address is this? Let's just take a look in a bit. So here let me just make this ARR of 0 now, and I'll copy this and I'll paste this 4 times. This is 1, 2 and 3. So let's just go back to this and compile once again, and if I run this now, this actually gives me some 0x1 2 Alright, so this thing actually stands for the value of the 0th element, and I don't want that, sorry about that. So let me just add ampersands here, and let's just go ahead and compile it once again. So as you can see, I got 4 addresses here, and if you look at this carefully, this address matches the one that we got when we had just written the name of the array. So that means that the name of an array actually gives you the address of the first element, which kind of makes sense because later elements can then just be accessed from the starting element. So that's the first thing, and as you can see, these 4 addresses that we got all have a difference of just 4. So this one is F0, this is an F4, this is an F8, and this is an FC. That's because C is actually 4 numbers after 8, because it goes 8, 9, A, B, C. So these are all 4 bytes apart, and the reason for that is because this is an integer array, so each value is going to take each value is going to take 4 bytes, so that's why these are 4 bytes apart. But what we must note is that these are consecutive memory locations and not just randomly scattered around. So that's another thing that I want to point out. And alright, at this point I just want to introduce you to some different notations here. So let's just make this a %d, and let's just try doing something like 0 of ARR. I know this doesn't make, sorry about that, I know this doesn't make too much sense, but let's just go ahead and try compiling this. And as you can see, I actually got no error here. So let's just run this as well. So if I do that, it actually prints 1, which is my expected output. And let's just copy this and try this differently. Let's try 1 of ARR, and let's just save this. And if I get a 2 here, that actually proves that if I write ARR of 0 or whether I write 0 of ARR, these actually just mean the same thing. This second one might not make sense, but I just wanted to tell you that it is also syntactically correct. We actually just prefer using this one right here. So another notation that I want to introduce to you is what if I write star of ARR. So as you remember, ARR, as I just told you, ARR actually is the address of the first element, which is the address of this one, and this is read as at address. So at address ARR, and ARR is address of 1, so at address ARR is just that one right there. So let's just try running this, and as expected I get a 1 here. So but this time, how do I access the next element, which is index 1, this 2 right here? So what if I do something like ARR plus 1? What do you think I'm going to get? If you remember our discussion about pointers, you'll know that adding a 1 to an integer pointer actually gets me to the next integer. So this adds a 4. So this ARR plus 1 is actually the address of this 2 right here, and let me just prove that to you. The way to do that is, actually let me just prove it to you by writing something like this. Let's just print both of these, and let's just make this %p, and let's clear this out. So as you can see, I got the exact same thing. So That's because this is the address of index 1, which is this number 2 right here, and ARR plus 1 is also the same thing because ARR is an integer pointer, so adding a 1 to it actually takes it to 4 bytes ahead. So the way I would access this 2 right here in this notation is just to add a star here, but I want to add a star not to ARR but to this whole thing, so I give a parenthesis here. Actually, let me just try doing this and see what happens, but before I do that, let me just change these values to 10, 20, 30 and 40. That'll make it simpler to talk about these and also understand it. So let's just go ahead and compile this. This needs to be a %d, sorry about that. So as you can see, I got an 11 here, and the reason is because it took the value at ARR, so it said at address ARR, that's a 10, and add 1 to it, that should give me an 11, which is what I get here. So if I want this at address to be applied to this whole thing, I just need to add a parenthesis here. So if I do that and if I run this now, as you can see, I got 20, which is the second element. So this is actually index 1 because this is index 0, index 1, index 2, index 3. So if I wanted to access index 3, I would just write a 3 here. And let's just try doing this. So as you can see, I got a 40, which is index 3 or my fourth element. So that's another notation that I wanted to tell you about, and I hope these notations are somewhat clear to you. Don't worry if you don't understand each and every part of this completely. You'll get there in time, but just remember that array elements are stored in consecutive memory blocks, and just remember that the name of an array gives you the address of the index 0. So we'll talk a bit more about arrays in the next video, so stay tuned for it.